In this film, it will be shown how aerial surveys and photo interpretation expedite the discovery and evaluation of geologic resources, such as minerals, fuels, and materials. Other films in this series include an introductory film, one on forest resources, and one on water resources. The economic well-being of a state or nation is often dependent, to a large extent, on its resources of minerals, fuels, and construction materials. The discovery, evaluation, and proper use of such resources may provide for a state or nation and also assure social and economic security for its people. The search for and evaluation of these natural resources is the task of the geologist. The task is frequently difficult, time-consuming, and expensive, and the geologist must make use of any developments that will make his work less costly, less difficult, and more reliable. The modern methods discussed in this film reduce the amount of time spent in field work. Geologists have learned that their task can be expedited by using such modern facilities as aerial photography and photo interpretation, the airborne magnetometer and scintillometer. The airborne magnetometer is a widely used instrument for rapid geophysical studies, and the interpretation of its readings is useful in locating geological resources. An instrument, the airborne scintillometer, is very useful in the search for radioactive minerals. The use of these airborne tools for geologic exploration is a new and expanding development. It is the primary purpose of this film to demonstrate the use of photo interpretation in the discovery and evaluation of geologic resources. In many parts of the world, there are vast unexplored or underdeveloped areas, difficult to reach and to traverse on the ground, and in which important deposits of mineral resources may be found. It is especially in these areas that the interpretation of aerial photographs can be used to the greatest advantage of the geologist. Fortunately, much of the Earth's land surface has already been photographed from the air. Ordinarily, copies of available aerial photographs can be obtained at nominal cost from the agency of government or private firm that has custody of the aerial negatives. This map shows the worldwide extent of aerial photography as of 1957. Other maps and reports may be obtained that contain the results of airborne magnetometry and scintillometry surveys. If photography is unsatisfactory or not available, new aerial photographs may be obtained from private firm under contract. In drawing up specifications for such a contract, the geologist should make sure that he obtains the combination of scale, film, lens, filter, and flying height that will produce the best resultant photographic image for his particular need. To plan his study, the geologist will obtain all the available maps and reports of the area to be studied. Of special importance are base maps of sufficient accuracy and appropriate scale upon which to plot information to guide his investigation, and reports that contain geologic data in the area may save him many hours of search. Here the geologist reviews the maps and reports and carefully plots on a selected small-scale base map all of the geologic information contained in the reports. He collects, in addition to the geologic information, data on climate, terrain, and vegetation. These factors are important because they affect the appearance of different rock types on aerial photographs. With all the geologic data visible at a glance, the geologist may be able to detect incorrect information because it does not fit the general conditions that are required. Data from ground or airborne surveys are also added to the map. For an overall examination of an area for plotting large features as an index for aerial photographs, a mosaic is made. A shingled or uncontrolled mosaic is made by matching the overlapping images and stapling the photographs in place. It is best to staple them so that the numbers are exposed, and loosely, so that individual photographs and stereo pairs may be removed for closer examination and study. When the mosaic is completed, all of the geologic information previously gathered by studying the literature is plotted in place on the mosaic. Definitely known information should be plotted differently than poorly or incompletely known data. For example, known geologic contacts may be indicated by a solid line, and uncertain contacts by a dashed line. The geologic study of an area involves the delineation of all geologic information. However, this film will deal with geologic studies devoted primarily to the search for mineral resources. The most important of these resources are metallic ores, fuels such as oil and gas, and construction material. Therefore, the geologist notes on the mosaic those areas most likely to yield these mineral resources. Ores are most likely to occur in areas of intrusive igneous rocks, such as granite. Oil and gas and construction materials are found in sedimentary rocks. The first step is to differentiate on the mosaic areas of intrusive igneous rocks and sedimentary rocks in order to localize the areas where intensive ground investigations will be made. Areas of intrusive igneous rocks exhibit somewhat distinctive features on the aerial photographs. While no one of these features is in itself diagnostic, the appearance of several together is a strong indication of the presence of this type of rock. These criteria are: the rock is generally light-toned on the aerial photograph, it is frequently very profusely fractured, and the fractures may be distinctly curved. Even in a heavily wooded area, the light tones and fractures may be seen. In such an area, a knobby, rugged topography may develop on the granite. The knobs are generally of about equal height when viewed under the stereoscope. A radial drainage pattern, which may be only visible under stereoscope, is likely to develop around such isolated knobs. There is no bedding of igneous rocks as there is in sedimentary rocks shown on this photograph. Bedding is, in fact, the strongest indication of consolidated sedimentary rocks. Here, bedding is seen in a region of high relief. In this scene, bedding is visible in folded consolidated sedimentary rocks in an area of moderate relief. Notice that the individual beds may be marked by a characteristic tone on the photographs or a distinctive drainage pattern. Distinctive tonal features enable bedding to be detected even in areas where the consolidated sedimentary rocks are horizontal, such as is shown here. Closed vegetation patterns may also indicate horizontal or gently dipping rocks. In areas of heavy tree cover, bedding may still be detected, especially when the photographs are studied under a stereoscope. Here, the bedding is indicated by the breaks that can be seen in the slope. Not all sedimentary rocks are consolidated. Some consist of loose gravel, sand, silt, and clay. Such sediments are seen on this photograph. Note that no bedding is visible. The area has a generally uniform or nearly uniform tone, except where cultivated, and there is no ridge alignment or strong drainage alignment as in many areas of folded consolidated sediments. Using all of these criteria, as well as the information from the literature previously plotted on the mosaic, the geologist systematically outlines the areas of intrusive igneous rocks and sedimentary rocks. These may, of course, be areas in which both sedimentary and igneous rocks are present, and it is well to indicate these areas separately. Where identification of rock types on the mosaic is difficult, photographs of that area may be studied under the stereoscope. The photo numbers are noted. Selecting the required stereo coverage, the geologist studies the problem area in detail and later transfers the information gained from this study to the mosaic. When the igneous and sedimentary rock areas are delineated on the mosaic, the geologist is ready to begin his systematic search for likely sites of mineral resources. By referring to the photograph numbers on the mosaic, the geologist can select specific aerial photographs covering the igneous or sedimentary rock areas. A study of these photographs will provide details of geologic structure and associated rocks that will aid in the final evaluation of the area. In this case, the geologist has decided to first study areas of consolidated sedimentary rocks for oil and gas. While mapping the geology on the photographs, the geologist makes use of the information which has already been gathered and plotted. In the search for oil and gas, structures such as anticlines or domes, which are likely sites for oil and gas accumulation, are sought. Different formations may be distinguished by their expression on the photographs, as shown here. Notice how the resistant formations make ridges and the less resistant formations between make valleys. The geology is mapped in detail. As in all geologic mapping, a stratigraphic section must be established as early in the work as possible. As his study progresses, the geologist prepares a stratigraphic section from his analysis of the photographs of the study area. A convenient scheme for differentiating geologic formations on the photographs is a compilation sheet, such as this one. Examples of column headings that may be used are tone. This is a shade of gray or white or black in which the formation appears on the photograph. Tonal texture. This refers to the appearance of the tone, such as uniform, mottled, or streaky. Resistance. Under this is noted whether the rock is very resistant and forms high ridges, less resistant and forms low ridges, or weak and underlies valleys. Vegetation. Under this heading, the type and density of natural vegetation is discussed. Drainage texture. In areas of fine drainage texture, the streams are closely spaced, and in areas of coarse drainage texture, the streams are widely spaced. Erosional form. Describe briefly the shape and form of the land produced by this formation. Under the last column, list any special distinguishing features. Another formation may show scattered clump vegetation or salt and pepper effect. Formation 1 is usually the lowest or oldest formation exposed in the area, and formations are numbered consecutively. The entire stratigraphic section can only be delineated by a careful study of the entire area. The exact lithology of each formation must be determined later in the field. Mapping the formational contacts and describing the stratigraphic section of an area, the geologist produces a photogeologic map. The strike and dip of the bedding and the thickness of the formations are estimated and recorded. A simple parallax bar may be used to help determine the thickness of formation and amount of dip. Structures are also indicated, such as this anticlinal nose, and this possible fault. Proceeding systematically, the geologist prepares a geologic map of the area of consolidated sedimentary rocks. At a later stage, the final geologic map will be compiled. On the other hand, in areas of unconsolidated rocks, there is no attempt to map formations. In such an area, a drainage map is compiled because the drainage pattern may be interpreted to indicate buried geologic structures. The search for ore minerals in areas of intrusive igneous rocks is facilitated by the preparation of a geologic map. The required photographs are selected from the mosaic. Such a map may be prepared by tracing the contacts between different types of rocks, and between the igneous rocks and the surrounding sedimentary rocks, as observed by stereoscopic examination. Major zones of shatter or faulting along which ore deposits often occur will be plotted. Local plugs intruded into the main igneous mass are marked. Of particular importance in localizing important accumulations of ore minerals is limestone in contact with igneous rocks. These areas should be specially marked on the map. This photograph shows the typical appearance of limestone on an aerial photograph of a moist region. Note the characteristic solution features such as sinkholes, streams draining into but not out of sinkholes, and also the mottled tonal pattern or texture, and the coarse drainage texture. Many of the world's most important ore mineral deposits occur in limestone, which is intruded by igneous rock. Proceeding systematically, the geologist maps the areas of igneous rocks for later compilation into a map. The next step in the evaluation of a region for geologic resources is the compilation of photogeologic map. If a suitable base map is already available, the information marked on the photographs may be traced onto the base map by a sketchmaster. If no base map is available, one may be prepared by tracing details from the mosaic. Roads, railroads, and large streams are traced to provide planimetric control. Each photograph is placed in the sketchmaster and adjusted to fit the base map. This rectifies some of the photogrammetric errors, and the geologic detail can be compiled into a map. All detail from the photo interpretation, airborne instrument surveys, the literature, and other sources is also put on the final map. When this map is completed, the first evaluation of the area for geologic resources begins. The evaluation of an area for geologic resources is a complex and difficult task. In addition to the geologic maps, all other sources of information must be used. The areas of igneous and sedimentary rocks are evaluated. It is the purpose of these evaluations to concentrate the field work first on the most promising parts of the area, reducing the time of the field evaluation and increasing the probability of locating resources. Here, the geologist is studying the map of igneous rock areas to assign priorities to parts of the area for later field check. Highest priority is generally given to places where limestone is in contact with intruded igneous rocks. These localities may be sites of contact metamorphic ore deposits. Data from airborne magnetometer surveys may aid in selecting the most promising of the limestone areas. Other localities selected for field investigations are major faults or zones of faulting, which may localize veins containing important ore minerals. Dikes and groups of dikes are also given priority for field inspection. Localities selected for field investigation are carefully indicated on the map. It is helpful to obtain the opinion of other geologists concerning one's own conclusions. The evaluation of areas of sedimentary rocks for oil or gas is performed by selecting anticlines, domes, and faults. The actual discovery of these fuels must, of course, depend on drilling. The search for anticlines and domes is carried out by different techniques in areas of consolidated and unconsolidated sedimentary rocks. This diagram illustrates structural closure. Closure is the vertical distance between the lowest and highest closed structural contour, shown here by the red lines. This figure illustrates a structure with large closure, and this illustrates a structure with small closure. By observing the dips of formations and size of structures on the geologic map, the geologist can select the anticlines and domes of highest closure. These are given highest priority. If any subsurface information from previous drilling or geophysical exploration for oil is available, it may allow further establishment of priorities among the structures of large closure. In areas of unconsolidated sediments, a drainage map is compiled. The prepared drainage map is studied for indications of structure. Some indications of structures are these: a radial drainage pattern developed around an uplift, the deflection of drainage around an anticline or fault, deflection of several streams around an uplift. Here are some typical examples of deflection of streams around uplifts. Streams may be ponded upstream from an uplift. Streams may change their meander habit over an uplift. Using these criteria, the geologist notes localities of possible uplifts, such as anticlines, domes, or faults, within an area of unconsolidated sedimentary rocks. These localities are best evaluated by subsurface methods, such as drilling or seismic exploration. While studying unconsolidated sediments, the geologist should be alert for deposits of sand, clay, and gravel, which are important basic construction materials. One of the most important sources of these materials are stream terraces, such as is shown here. These terrace deposits may be clearly seen on aerial photographs under the stereoscope. Here the geologist is outlining an upland terrace likely to contain sand and gravel. In this case, the geologist is carefully outlining a valley-side terrace which may also contain sand and gravel. In many cases, several terrace levels may occur in the same valley. When the geology has been completely evaluated and priorities assigned, a route for the field study is laid out. This route should be established to allow the most rapid and thorough confirmation of the photogeologic map and the determination of the exact lithologies of the igneous rocks and the sedimentary formations and details of geologic structure. Having completed his preliminary evaluation, the geologist is ready to begin the field study. In the igneous rock areas, a systematic search for ore minerals is made. The areas are explored in order of the priority which had been previously established. Information about the type of rock found is recorded and samples taken for later study. Special samples may be taken for particular types of analysis, such as in geochemical prospecting. The search is continued from area to area as previously selected. By using the aerial photographs, the geologist can locate himself very accurately. A careful search is made for gossans, or occurrences of common sulfide and oxide ore minerals, which may reveal the presence of large ore deposits. Throughout the field study, the geologic map serves as a guide. Careful notes and sampling are required for the final report and evaluation. In unconsolidated rock areas, the stream terraces mapped on the photographs are studied in the field to confirm the presence of gravel, sand, and clay. Samples are taken for analysis in the laboratory. In areas of consolidated sedimentary rocks, the geologist makes careful observations on the kinds of rocks mapped on the aerial photographs. Each formation, such as the sandstone shown in this scene, is examined in detail. Here the geologist is also testing the cementing material with a drop of acid to determine if it is calcareous. Notes are carefully taken classifying the various formations. Structural information, such as strike and dip of bedding, which had been estimated on the aerial photographs, is confirmed in the field, and the results are plotted on the map. Exact thickness of formations may also be measured. The selection of specific outcrops for field checking, like the dipping rocks shown here, is based on the geologic map made from aerial photo interpretation. Field evaluation is of course necessary to verify the photo interpretation and to complete the geologic map. When the field study is completed, the geologist returns to the office and prepares the final report. This report gives an evaluation of the area and makes recommendations. The prospective areas of ore, oil, and gas are listed in order of importance and promise, so the systematic search for these materials may be carried out. A suggested outline for this report is as follows. First, area studied. Here the area studied is located exactly, and the physiography is briefly described. Second, methods of study and sources of information. Methods of study by aerial photographs, airborne instruments, and field investigations are noted. Third, general geology. Stratigraphy and rock types and structures, but only large structures. Stratigraphy and rock types of the region are described, and the areas of igneous and sedimentary rocks discussed separately. Lastly, a list of most promising areas in order of importance is made. Here again, it is necessary to discuss separately the areas of igneous and sedimentary rocks. Detailed description of each area. Recommendations for further evaluations are made, such as large prospect pits for ore minerals and seismic exploration or drilling for oil and gas. final report and accompanying maps are submitted. By use of modern exploration tools, such as aerial photo interpretation and airborne instruments, the geologist has made a rapid evaluation of the potential geologic resources of a large area. With this detailed information, a search for specific minerals, for oil and gas, or for construction materials can be made as required. Although these tools that the geologist uses to expedite his surveys and investigations do not eliminate entirely the need for field surveys and careful ground investigations, they do indicate to him the areas in which his efforts should be concentrated and eliminate for him areas in which valuable resources are not likely to occur. This information greatly reduces the time and difficulty and cost of his fieldwork. The process of bringing these valuable assets to market, processing them, and using them in industry and commerce provides employment and income for many people. And when these assets are properly used and conserved, they can be made to provide an expanding and lasting social and economic prosperity for the people of a local community, a state, or a nation.